So our translator uses all 5 buttons as inputs. This is the dot, the dash, the space, the enter, and the reset up top. Each button will have its own LED that lights up to indicate it's being pressed. On the leftmost side, this is the dot, dash, space, enter, and reset, which will reset everything to 0. So we'll use the dot and dash buttons to input a Morse code sequence, and then once we click the enter button, an 8-bit ASCII value will be represented by the 8 rightmost LEDs on the board, where the LED will light up if the bit value at that position is equal to 1. For example, I'll show the letter A, which is a dot and a dash, and then this 8-bit value is equal to 65, which is the correct ASCII value for the letter A. I'll reset it and do the letter B.
Yeah. Can we do that?
And then the letter C. In addition to the LED display, we're also using a VGA screen to display our letters, and the letter will appear after we click the enter button. So I'll show a few letters. And then we also have a separate space button, and a couple spaces, and then we also have a period, which is represented by 4 dashes. So our VGA screen can display up to 50 letters at once. So once we hit that max 50 letters, once I try to continue to input a letter, nothing will appear. So you'll have to use the reset button to clear the screen, and then you can begin with your next input.
So for our top _2 module, this module contains the translation of the Morse code to the letters. So we input 3 buttons, a dot, one for the dot, dash, enter, and space, and then we output the letter, which is an 8-bit ASCII value of the corresponding letter. And then we have these outputs, the ready, check, dot for the dash, and the space, just as like LEDs to just check if the certain button is being pressed. We also output a button enter positive edge, and this is then used for the VGA controller, which will be explained further, this output. And then we have a 6-bit Morse code register, which stores the Morse code sequence that's entered, and a 4-bit code link that contains the length of the Morse code. So we first debounce each of the buttons, the dot, dash, enter, and space, and we output a positive edge stable signal for each of these buttons, and then we use this signal for our button logic. It becomes high at a positive edge and remains high for 1 clock cycle, and we want it to use this because this ensures that our button presses will be registered only once for a clean and reliable signal. And we have all our button logic in a negative edge always block, and we want to do this because when it's the negative edge, since all the buttons are positive edge triggered, they will already be at a reliably high signal. So this will improve our accuracy. So when our button dot is pressed, we have the 6-bit Morse code shift 1 to the left and a 0 be appended to it, and if it's the dash, we append a 1 to it. The code length increments accordingly to each button press, and if the space is pressed, we set the Morse code back to 0 so that a new input could be made, and then we also set the letter to the specific 8-bit value. This is just a value that we set it to. It's not necessarily the one used for a space, but it's just the one that helps us to find the correct display in our ASCII room, which will be explained further. So then once the enter is pressed and you finished typing your letter, you compare the Morse code value and the code length value, and depending on what it is, the letter variable will be assigned to its corresponding letter. So for example, for the letter A, the Morse code is a dot and a dash, so the end is a 0 and a 1, and the code length is 2, and you can see that here, and so A will be assigned to letter, and this is actually the ASCII value A that's being assigned. So we go ahead and do this for all the letters, and at the end, this last else if statement is for a period. Again, same with the space bar, we just assigned it to this 8-bit value, and this will be shown. It just corresponds to the correct. It's just a way to find which one it is in the ASCII round, which we explain further. And so in our VGA controller module, we are inputting the button enter, and we are also having the letter as an input, and these are both coming from the top _2 module. And then we also have a horizontal sync, vertical sync, and an LED on in order to display all of the letters, as long as a clock and a reset. So we set some parameters originally, which are the as you can see. One important one is the max underscore letters, and this sets, you can obviously change it, but we set it to 50, and this is going to be the size of our memory array. So we have this memory array that stores, so you can see it right here, which is going to store all the letters so that when every time you enter a new letter, all the letters will appear on the screen. We also have a letter position array, and this is going to store the X positions of the letters so that we can move it along the screen and have it knows where to stop, like where the last letter has been. And then we have the current X position, which is going to have the position of the new next letter so that knows where the next letter should be displayed. So if you go here, you can see that we get the letter output, and based on that letter output, we first, based on that letter output, these are all like the letter outputs that we had in the top underscore 2 module. Based on when we set our adder roam variable to a specific value right here, and this value corresponds to the value in the ASCII roam module. So let me give you an example to make things clear. So if we look at the third line here, this 8-bit value is the character value for the letter A. So we set our adder roam value to H410, and if you look in our if you look at our ASCII roam module, this value is, by having that set to that, it will display the letter character A. So this is our ASCII roam module. It just contains the outputs for each letter. You can see this here, and we also added a null, just a blank one for the space, as long as a period. So when the adder roam value is set to that and it's passed to the ASCII roam, this is the image that we will see on the VGA. So this is our main logic to display all the letters. So if the button enter is pressed and the letter count is less than the maximum count, so the array is still like not full, the memory array will store this letter at that specific iteration value. The letter position will have the take in the position, and we have a letter count to keep track of how many letters we have entered, so we don't pass the max value, and that keeps getting iterated. And we also iterate our current position value by a character width, which we set to 8 bits. So that is how we display all the letters. So then when we're passing it to the adder ROM, it's looped through the memory array, so it displays all the letters. So we have 2 enable wires that these, when they're activated, will make sure that the LED will display the letter. You can see this logic is demonstrated right here. And the font ROM is the output of the ASCII ROM module, so it will display the LED. The LEDs will display the specific letter, which is the output. So these enable signals, we have 2. The enable one, this just checks the entire VGA screen and make sure that it's in that specific region. So we can set specific values. We set these right here. And then we have that the letter enables, and this signal just is an array of signals, and it's generated in this generate function, and it's an array of signals that activates the relevant character when the current pixel is within its bounding box. Within that certain box, it will activate that pixel. So these 2 enable signals will activate the LED, and that will display the letter. So this is our VGA controller module, and then in our top module is where we call both of these